Hi, Chris Good here, and we're going to talk about one-way ANOVA. So we've already discussed in class why you need to do an omnibus test to look for significant differences among more than a couple of means, because if you do a bunch of t-tests, you will inflate the likelihood that you'll make a type 1 error. And to find out exactly how likely that is, you can take the number of paired tests that you want to do, number of t-tests you want to do, and each one of those carries with it a 0.95. If you're using 0.05, it carries with it a 0.95 chance of not making a type 1 error when the null hypothesis is true. So if you multiply those by, take those to the exponent of the number of times that you're doing those tests, here we'd have to do 3 different t-tests, then you'll get the cumulative probability of not making a type 1 error, and you'll see that probably gets smaller and smaller. 1 minus that quantity then is the cumulative probability of making a type 1 error, so at least one type 1 error. So we've done that in class. Here we're talking about this Mozart study. We're adding a third condition of listening to Metallica in addition to silence and Mozart. And when we think about this in terms of a linear model, we need to create dummy codes to account for all of the groups that we have. So we've already looked at dummy coding for the event of 2 groups. So like if we were only doing Mozart versus silence, then we'd use this linear equation here. If we're predicting IQ, there'd be some intercept, b sub 0, which would be IQ when you're listening to nothing, because that dummy code would code Mozart this x value as 0. That would mean its IQ would be predicted by your b0 mean, b0, which is the mean of the silence group, plus nothing, and that would be your group. If you have Mozart coded as 1, you listen to Mozart, so your IQ would be equal to the silence mean plus b sub 1 times the Mozart code of 1. So b sub 1 then becomes the difference between the mean of the Mozart group and the mean of the silence group. Similarly, if we add a third factor into here, a third predictor, we get coding for the Metallica group. So if you listen to Metallica, Metallica gets a value of 1. Mozart gets 0 because he didn't listen to Mozart. You listen to Metallica. So then your IQ is b sub 0, which is the silence mean, plus 0, Mozart is 0, plus b2 times Metallica code, which is 1. So b2 then becomes the difference between b sub 0 and the Metallica mean. So all of that is listed here on this next slide. All right, so b sub 0 is your silence mean. And it says placebo here. What does the silence mean? B sub 1 is the difference between the Metallica mean, which is up here, and the silence mean down here. And B sub 2 is the difference between, this is Mozart, sorry, and this is silence. B sub 2 is the difference between the Metallica mean and silence. So there. The dummy code table then looks like this, where if you listen to Mozart, if you listen to silence, you're in the silence group, then Mozart gets a 0, Metallica gets a 0. If you listen to Mozart, Mozart 1, Metallica 0. You listen to Metallica, of course you didn't listen to Mozart, so 0 here, and 1's for Metallica. So those are the values for B sub 0, the silence mean, B sub 1, the difference between that silence group and the Mozart mean, and B sub 2, which is the difference between the silence mean and the Metallica mean. So there's 3 values that we really need to consider and that I'd like you to understand the meaning of when we're talking about ANOVA, either as a linear model or sort of the old way that we've come to think of ANOVA. And the first one is the total variability in your entire data set. So if we look at the mean of all of the scores, right, it's called the grand mean, and it's represented by this line here. There's some distance of each score, regardless of what group folks were in. There's some distance between each score and the line. We can measure that distance. You'll probably guess that I'm interested in squaring those distances. And we sum all those, so we get the summed squared deviations of each point in the entire data set from the mean of all of those points, which also happens to be the mean of all three of these means as well. So that's the distance of each point from the mean of y. So that's the total variability in the data set. That's the total sum of squares, the total summed squared deviation of each point from their common mean. When we're considering Anova as a linear model, the residual variability, the residual sum of squares, has another name. It's called the within treatments sum squared deviation within each treatment. So we have three treatments here. We treated folks with silence, treated them with Metallica, and treated them to Mozart. And within each group, there's a mean, right? And we have 5 scores in each group, and there's some distance of each score from the mean. So if we sum the squared deviations of each point within a group from the mean of that group, right? And then we add in the sum squared deviation of these points, the Metallica points, from their mean, and we add in the sum squared deviation of each Mozart score from the Mozart mean. We get the total within treatments variability. And we're going to come back to this in a second and think about what this means, but for now, understand that this is variability within treatments that could be due to any number of things. Individual differences, right? These are 5 different people here. It could be due to random chance, sort of this person happened to have a high IQ, this person happened not to eat their breakfast cereal, etc., etc. So this variability within treatments that's kind of random. It's not systematic. It's not due to the treatment because within a group, everyone was treated the same. All right. This is the same as the residual sum of squares. Like if we had a regression line that was just fitting all of these points, right? Without putting people into groups, there would be some measurement that we could have a regression line passing through all these points. There'd be some variability around that line. Here, we don't really have a line. We have these 3 points, and they're not connected by a regression line, so we're looking at variability within each group. Remember, these aren't sort of spread out around here. The variability is all in one condition. We've only separated the points so you can see them. The variability is all sort of vertically around this mean, around one x value, which is their group membership. Okay, so we have total variability, variability around the mean of all of the points, the grand mean. We had within treatments variability, variability within each individual group, but all summed together, so it's total summed variability within treatments. And finally, we have variability between treatments. So this is simply the variability among these 3 means. And the way we compute it is it's sort of a weighted version of the distance of each mean from the grand mean. Right? It's the summed squared distance of each mean from the grand mean. It's not calculated exactly like that, but that's what you need to understand at this point. So really, this is a measurement of how different these means are from each other. And we'll come back to this in a second, but think about why people in the silence group have an average score that's different from people in the Metallica group, which itself is different from the people in the Mozart group. Why are the averages different from each other? There are different people in this particular type of design. It's an independent groups design. But they also were treated differently. So there's some random aspect of it, or chance aspect of the variability among the 3 means. But there's also a potential treatment effect, and that's really what we're interested in. So just like the Anova from before, we're going to divide those measurements of variability, those sums of squares, the summed square deviations of all the scores from the grand mean for the total variability, although that's not pictured on this screen. We'll divide the residual sum of squares, right? That's variability within treatments, sum squared deviations of each score from their mean within a treatment. We'll divide that by degrees of freedom to get variance. And for the third one, the model sum of squares, which we're calling the between treatments sum of squares, we'll divide that by between treatments degrees of freedom to get variance. And what F is, it's the same as we've been discussing it. F is a ratio of one variance to another. It's the model sum of squares, it's the model variance, or mean square, which is the same thing, model variance compared to residual variance. It's the variance that may be attributed to your model, the fact that you treated these three groups differently, to the error inherent in that model. And if there really is an effective treatment, it should be many times greater than the error in that model. And F, of course, is the value we compare to the distribution of F. We'll get back to that a little later. The only other thing I want you guys to know for our upcoming test is why these numbers are different from each other. Why within the Mozart group, 7, 4, 5, 3, 6, why did everybody not get the same score? They all listen to the same thing, right? Well, they're different people, for one thing, right? So there's individual variability, individual variation. There's also an element of chance involved that's not attributable to them necessarily being different people, but they have different experiences, and although this person may have a high IQ, they just weren't trying, or they didn't care, they became distracted. There's random variability there. So chance and, I guess, people are different. Same for the Metallica group. They all listen to the same thing, but they're different people within this group. But there's a role of just random variability as well. Same thing for the silence group. Different story for why the means are different from each other, because although these means do come from different people in an independent group's design, right? People who listen to silence were different from people who listen to Metallica, so that's one reason why their mean might be different. Chance is also a factor, because folks, we might have randomly assigned maybe smarter people to be in the Mozart group just by accident, however unlikely that is. But the third reason for these means being different from each other, which is the possible treatment effect, right? It may be the case that what we're asking them to listen to affects their average score. So we measure variability within each group by sum of squares, the residual sum of squares, our error sum of squares, which we're now calling within treatment sum of squares. And we measure variability among the three means by sum of squares between treatments. So when we do the Anova, right, we're assuming that all of these sample means, right, the three means that we're comparing came from populations that had means that were equal to each other. Oops, move that around there. There we go. And under that null hypothesis assumption, we look at the variability among the three means and compare that to variability within each group. And when the null is true, sometimes you will get samples with means that are much more different from each other than the scores within each group are from each other. It's unlikely, but sometimes it happens. We call them mean squares, but really they're just variance. So, these two quantities, if I can go back a few slides, these two quantities are actually the two parts of the total variance, right? So the model sum of squares and the residual sum of squares, and we're just looking at how big one is with respect to the other. When the null is true, most of the time you'll have F's that are pretty low, right? Under some degrees of freedom, this peak here is sort of equals out the numerator and denominator, and it's close to 1. Sometimes you get means that are very, very different from each other, more different than the scores within each group are different from each other. It's unlikely, but sometimes when the null is true, it happens. Of course, this is the F distribution that we compare our F to. That's all that I want to cover before our test that's coming up, but that main thing that I want you to know is how to dummy code things and what these numbers represent in the F ratio. What the variance of your model, right, the between treatments variance, and the within treatments variance stands for. the reason why these scores within a group are different from each other. Same here, same here. And the reason why these means are different from each other. So certainly shoot me an email if you have any questions. We'll also have a chat review session Monday evening. And thanks for watching.